Okay, can you see the spec overview?
Yes.
Yes.
Cool. Okay, so this, Bucky, have you started recording?
Yeah.
Cool. This is just the overview document. It's mainly just a copy of the README, but I think it's still useful to go through to start. Yeah, so the IAVL tree, it's a versioned AVL tree, so it's a self-balancing binary Merkle tree where all of the nodes are sorted lexicographically by their keys. And what I mean by versioned is that on each new iteration, like rather than mutating the key directly, we copy and then write any updates in like a new version. So that'll become clearer in like other documents, but that's just the broader overview for now. Yeah, so as I said before, the IAVL tree is a binary Merkle tree of nodes. So we store each node as this struct, marshaled. So it has a key and a value, which is pretty useful. The version of the IAVL that this node was first added in, so the version of a node might not actually be the version of the latest tree. If a version has been existing for the past 5 versions, it'll just have, if a node has been existing for the last 5 versions, it'll just have the version that it first appeared in, even if that node is still existing in later trees. The height of the node, this is just the tree height, where the node appears in. The size of the node is the number of leaves that are under the node. So you can think of this like in a fully filled out tree, the size is always like 2 to the power of the height. So on a height 0 node, the size is 1 because it's just a leaf node. On a height 1 node, the size is 2, and so on and so forth. Then there's the hash of the node itself, which is the hash of all of the above values, along with the hash of the left hash and the right hash together, if they are non-nil. And then we have a couple extra fields here for left node and right node, which just caches the child nodes if they've been accessed already. And this is just to prevent having to use the DB to retrieve the child nodes every single time using the hashes. And then we just have 2 Boolean flags here. The saved Boolean flag indicates that this node has been saved somewhere, either in memory or disk. And then the persisted flag is specifically if this node has been persisted fully to disk. And these flags are mainly useful in like the pruning PR that we might get to. So yeah.
I have a quick question. When you say it's saved to memory, what does it mean? It's already in memory, right? Or...
Yeah, the saved flag just means that it's saved either in memory or in disk. So if either of those are true, then the saved flag is true.
Okay, but they're talking about something else here, like additional contents, not this node, right?
Could you repeat the question?
No, I mean, yeah, this node, it's already in memory, right? When you say it's saved to memory, does it mean that
Sure. I mean that, so for the pruning PR, the tree, the IAVL tree itself, is either going to be persisted to a memDB or persisted to disk.
Oh, I see.
Yeah, so if it's persisted either to the memDB or disk, then it has the saved flag set.
Right.
I'm not sure we should use the word persisted here because it would not be persistent when it was saved. Maybe there's some better words that would be more indicative here. I think there's a little bit of confusion there.
Sure, yeah. Well, that was why this other flag exists, so that it's only persisted is only true if the node has gone all the way to the disk. But maybe
so saved indicates that there's another copy of this node somewhere in memory.
Yes.
Uh-huh.
It means that the IAVL tree that this node contains has been saved either in the memDB or on disk. Possibly, it'll possibly make sense like later in the spec when I talk about the node DB itself.
Can we just would the comment be clear if it just said saved in the DB, and the DB might just be a memdb, or it might be on disk, or it might be on another machine, or who knows? It's just the database.
Sure.
Yeah. That would clarify.
Yeah. I think that works. And then like I'll go over this again like in more detail once we get to the node DB, because that's where the pruning logic actually happens. So if there are questions there, then I'm happy to answer them.
Quick question. You said that the node version is the version of the tree when it was added. Is the version changing when it's modified, and what's happening on delete?
Yeah, so if the node itself is modified, then because it's immutable, this node will be copied with its version like incremented, and then any updates to that node are made in that new node and then saved to the DB.
Okay, and for delete?
For the, I'm sorry, I didn't catch the last bit.
If the node is removed?
The node might not be removed. It might just be like, it could, the older versions can still stay in the database, and like a pruning logic would determine when nodes get deleted.
I see. And also you mentioned the number of nodes is 2 to the power of n. Is this a fully populated tree?
That was an example if it was fully populated. So size is just indicative of the number of leaves that are under the current node. But in a fully populated tree, that will be 2 to the power of the height.
Thanks for that.
But it's not necessarily 2 to the power of the height.
Right. Okay.
Yeah.
So I also have a question here. So every node has this size field, right?
Mm-hmm.
So it means that whenever you include something, you have to update everything all the way up to the root?
Yes, there's on the set function, there's calc height and size that gets called, and that will update the height and the size values of any parent node of that.
But the height sometimes it doesn't change, but the size is going to always change whenever you include something, right?
It'll change all parent nodes. Yeah, it'll also change the. Oh yeah, it might not change the height every single time. But yeah.
Mm-hmm.
Okay. Are there any more questions or? Cool. So the inner node has keys equal to the highest key on the left branch, or they have their value set to nil. And yeah, the version of the node is the first node version that gets added in. And so this is how each node gets marshaled. It just, we write the height, the size, the version, and the key first. If the node is a leaf node, then it'll also have a value. So we encode the value in. If not, then we encode the left hash and the right hash if they aren't nil. So you can see that logic here. So if there's any questions.
Well, just to be clear, I would just point out that, you're seeing amino functions being used here, but which is effectively protobuf 3, but we're trying to encode a struct, but we're doing it one field at a time. So this actually isn't a protobuf encoding of a struct. It's just a bunch of fields encoded and concatenated next to each other. So there's no, none of the things that you usually get at a protobuf, like the field types and the numbering of the field types in a struct. None of that is here. You're just like raw encoding fields and concatenating them. So that's something that I would suspect is, we might want to change, but maybe for efficiency purposes, this is faster. But anyway.
Mm-hmm.
Sure. Yep. And then hashing, it works a lot like simply marshaling the bytes into the hasher, the io.writer. But there's a couple differences from how the node gets hashed and how it gets marshaled. So if you can see, just as before, we hash first the height, the size, the version. And then the key difference is that the key is not hashed in for inner nodes. So if you look at the code, it's if node.isLeaf, then we write, we hash in the key as well as first hashing the value and then hashing that together. And then if the node is not a leaf, then we hash in the left hash and the right hash. Are there any questions on how nodes get hashed?
Can you clarify what the keys are for inner nodes?
The keys are, the keys are, since the binary tree is a, it's lexicographically sorted on the keys, when the, I think I have it here. Yeah, so inner nodes have keys equal to the highest key on their left branch. So whenever something gets set, any of the inner nodes can have their keys updated to the highest leaf of the left branch.
So that's the rightmost great-grandchild of their left node.
Yeah, correct.
So to be precise, we're actually dealing with an AVL plus tree, where the actual keys are only stored in the leaves. So the inner nodes don't have unique keys, but they'll just have the key of the highest leaf on their left branch.
Yeah, the inner nodes just have, every inner node's key is equal to like some child's key, and precisely the highest, right? Yeah, right.
And the reason to have for the key of the inner nodes to be structured like that is?
So when you iterate, you can iterate on like key ranges pretty efficiently.
Yeah. Cool. And produce range proofs and so on.
Cool.
Everyone with that? Alrighty.
Yeah. And the saving and persisting code is just like a repetition of what was above. They may be stored either in like temporary storage, like a memdb, or persistent storage. And if either of those are true, then node.saved equals true. Otherwise, if it's persisted completely to disk, then node.persisted will also equal true. But I think that'll be clear once we get to NodeDB. But before we get there, I just wanted to like quickly talk about how the key format, which is how the nodes are actually stored in the database. So when I say that nodes are stored in either a memdb or a recentDB, they'll be stored under a specific key. And I don't mean the key of the tree itself. I mean the key that you use to retrieve the node in the database, at the database level. So for that, we use key formats. So like the node key format will be prefixed with an N to prevent collisions, and then it'll be appended with the hash. So if you want to retrieve a specific node from the database, you just prefix N, append its hash, and then you can retrieve that node from the database. Orphans is something we'll get to in the NodeDB documentation, but it'll be prefixed with an O again to prevent collision. And then orphans have both a to version and a from version, which you can kind of consider like almost reference counting. So an orphan is a node that got at some point removed from the latest version of the tree. And we have to still keep track of what versions of that of the IAVL tree refer to this node. So that's the to version and the from version, and then it's appended with the hash of the node. So for example here, like an orphan key of O53 and this hash means that this specific node existed in the IAVL tree from version 30 all the way up till version 50. So as long as there exists an IAVL tree between versions 30 and 50 in our database, we need to persist this node because that tree still refers to this node. But as soon as we've pruned all of the versions between 30 and 50, then this node is no longer referenced by an existing IAVL tree, and it's safe for us to delete it. So that's why orphans exist. Are there any questions on orphans? Okay, I think we'll go into more detail about them in the NodeDB docs. And then saving the root of the IAVL tree is just R, again, to prevent collisions, and the version itself. So if you want to retrieve version 5, you just query the database with R appended with 5, and you get back the root hash of the IAVL tree at version 5. Cool. So now, yeah, the NodeDB is responsible for all of the persisting logic for nodes, orphans, and roots, and it determines whether things should be stored in temporary storage or persistent storage, and it fully encapsulates all of the pruning logic that was passed into the IAVL tree. And the default behavior currently is to prune nothing, so every single version gets persisted completely to disk. And so the NodeDB maintains 2 separate databases and batches. There's a recent DB for temporary storage. That's typically going to be instantiated with a memDB. And then there's a snapshot DB for persistent storage, like a level DB, and that's to persist any snapshot versions. And then with the pruning PR, the NodeDB takes in a pruning strategy, and that pruning strategy will tell the IAVL how many recent versions it wants to save. And those will all be saved in memDB, and at what frequency to persist in disk. So every 100 versions, for example, the IAVL tree will persist that version all the way to disk. Okay, are there any questions on the structure? Cool.
Okay, so let me ask you this. So why is the size needed? The size of each
size of the IAVL tree? Oh,
yeah.
That's a good question.
No, you showed before some data structure that contains.
Yeah. Don't have that answer off the top of my head. Though I do think I've seen like its use in like the set, remove, and balance functions possibly, but I'll have to like look at them like into the specific documentation, and then I can answer that. But yeah, maybe I'll answer that offline in like the dev-tendermint Slack.
Yeah, don't you need it for balancing?
No, I don't think so. It's the height.
Well, you would need the height. You would need the difference.
Oh, you need the height. Yeah.
So like, yeah, it'll balance. The IAVL self balances whenever the balance is greater than 1 on either side. But I get to that later in the documentation. So yeah, the size specifically, I have seen it used, but I can't remember off the top of my head where. So I can answer that offline.
Okay.
Cool. Okay, so I'll go to just saving versions. So this is where we already have an IAVL tree that's like the current IAVL tree has been formed, and we want to then save it as a specific version. So the first thing that happens is that the NodeDB checks the version against the pruning strategy, and that will tell it whether it's a snapshot version or not. And it's a snapshot version, then anything that gets saved both to the recent DB and to the snapshot DB. So like all IAVL versions in the current pruning PR, they get like a snapshot version will get duplicated at least for a little bit, both in the memDB and in the level DB. So the first thing that happens is that we save the root hash under the root key R version, R appended with the version. And then any new node that got created between the last version and the new version gets saved under the node key. So it's important to note that we don't duplicate and save every single node. We just save effectively the diffs between the last version and the new version, because all of the nodes from the last version are already in the NodeDB under this key format. So the current IAVL tree just has to refer to them like as with this hash, and then they can simply get retrieved even though they were added in previous IAVL versions. And that works because in the node struct, we have access to the hash. And so we can always retrieve the full node from the database that way.
But all new nodes get saved to both the recent DB and the snapshot DB?
Only if it's a snapshot version.
If it's
Otherwise,
snapshot version, yeah.
Only if otherwise it'll only get saved to the recent.
But if it's a snapshot version, some of the nodes might be new with respect to the recent DB, and a lot more might be new with respect to the snapshot DB.
Correct. And in that case, all of the nodes that are new in the recent DB will get saved to the recent DB, but all of the nodes that are new to the snapshot DB will get saved completely written.
Uh-huh.
So there's the code handles that case, which is always going to be the case, that there are nodes that are new to the snapshot DB, but not to the recent DB.
Right.
Yeah.
And what triggers a new version?
A block.
Yeah.
Oh,
so on each block, the commit will.
I see.
Yeah. So the commit will like save that tree, that working tree, as the new version, and then we'll clone the working tree for the next block, and then the next block will use that as a working tree and make updates to it on each transaction, for example, and then on that commit, it'll like save that as the version +1.
And when you say that you clone the tree, essentially clone it on demand, I suppose. So you just copy the root and then the rest as needed.
Yeah, just copy the root and the pointer to the node DB.
Okay.
Yeah, and then from the root you can access everything else.
Right. Either in an earlier version or I don't know, the current version, depending on what nodes have been created.
Yeah, the root will access can access all of the nodes in the current version, and then the nodes in the current version themselves might have been added in previous IAVL trees.
Okay.
Okay, so any old nodes that were part of a previous version IAVL but are no longer part of this one have been saved in an orphan map in the current IAVL tree. So we'll see that later, but in the working tree, any updates that change a node or make a node no longer part of the current IAVL tree will get saved into this orphan map under the key orphan.hash, and it'll point to the value is the version of that node. And then this map gets passed into the save version function. And so the node DB can iterate through this map and store every orphan node under the key O to prevent collisions, and then the to version and the from version. And the to version is the current version -1, because if the node got quote unquote deleted in the current version, then it existed all the way up until the current version -1. And then the from version is the version at which the orphan got added. But we already know that from the value in this map, orphan.version, because the node's version value will be the version that the node got added into. Does that make sense, or should I try and repeat myself? We're basically saving in the key itself the range at which this orphan existed in the IAVL tree. So it existed all the way from to version to from version, and we can get that information in the save version function because we know the to version, which is the latest version -1, and we know the from version, which is just the orphan.version that we have in our orphan map.
And you said that this is part of the key, right?
Yeah, this entire thing is the key that will store the orphan node itself in the IAVL tree.
So the reason why
I misspoke. This mapping, this key value pair gets stored in the IAVL node database. So we have this O to version from version, which defines the range for which the orphan exists. And then we have the orphan node hash here as the value that gets stored. So we can retrieve the orphan node by simply retrieving the value from this key, which will give us the node hash. And then we can prefix this node hash with n, as I said before, like this way. And then we can get back the orphan node itself.
Okay.
So this is
can you perhaps explain sort of the motivation? Because I guess this has to do
Sure.
with how then to search for the versions and the orphans.
Perfect, yeah. So the motivation here is for the deletion algorithm. So all the orphans need to exist. So it's really a question of how long should a node stay in the database? And a node should stay in the database so long as there exists an IAVL tree that refers to it or that contains it. So we know that this node was referenced by an IAVL tree between to version and from version. So any IAVL tree that is between from version and to version has this node as part of its IAVL tree. So the node should stay in the database so long as there exists an IAVL tree that has a version between these two values, to version, from version. But the moment that all of these versions get deleted, then we know that this node is no longer needed. No tree references it, so we can then delete this node. So that gets a lot clearer in the deletion documentation, which we'll get to pretty soon. So, are there any questions on how the tree itself gets saved? Okay. And so the saving of orphans works differently depending on the pruning strategy that you pass in. So if the pruning strategy is not the default one, so there's a frequency that is greater than 1, then we don't actually need to store every single orphan into the snapshot database. We only need to store an orphan into the snapshot database if a snapshot version exists between an orphan's from version and a to version inclusive. The reason for this is because the orphan node is tracking whether there exists a tree in the database that refers to that node. And if there is no snapshot version between the from version and to version inclusive, then we also know that there's no tree in the snapshot database that refers to this node, so we don't even need to save the orphan there. So the code for that is just here.
I have a question here.
Yep.
So the orphan node is stored with the prefix O, and it's also stored with the prefix N. Then we want to query it hash. Is that correct?
No. So this is kind of like a indirect way to retrieve the orphan node. So I want to, it'll be clear when I get to deleting versions, but I can talk about it really quickly here. Let's say I want to get all of the orphans that got orphaned at version 10, for example. I know that they got orphaned at their to version is 9. So then I can just iterate in my database over all of the keys that start with O and 9. That will give me the node hashes of every orphan that got that version. And then all these orphan hashes, I can then use to retrieve the node itself. So it's kind of like an indirect pointer.
Okay, so node itself is stored with the prefix N.
Yeah. The node, like the marshaled value of that node, is stored under the prefix N. And then this hash specifically is a value that gets stored under the key O2 version from version.
Okay.
Whenever node gets orphaned.
Okay.
Yeah. So the node like marshal value only gets stored once. Cool. Right. So now there's the deleting logic. So, the first thing that happens when a version is deleted is that the root hash corresponding to version v is deleted from the node. And then what we have to do then is all orphans whose to version equal to v. Okay. All orphans whose to version equals the deleted version will get their to version pushed back to the highest predecessor of v that still exists in the node database. So to make that more concrete, let's say you're trying to delete version 10. Any orphan whose to version equals to 10 will then get their two versions pushed back to the next highest number. So for example, let's say the next highest number is 8 in the node database, then all of the orphans whose to version was once 10 will get deleted and resaved into the database with to version equals to 8.
So this is going to edit the effectively the key for each orphan.
Correct.
And these are all in the database.
Yes.
Wow.
And move this to version down.
So this is probably the source of a tremendous amount of write amplification.
Yeah.
Uh-huh.
Mm-hmm. So they are like relatively small writes, but there are a lot of writes.
It becomes a lot of writes because it's level DB under the hood, right?
Yes. Yeah. If the version itself is a snapshot version, or yeah.
Oh, okay, so I have a quick question here in this regard. So do you guys believe that the AVL is an important part of the overhead?
I think it's the major part besides the
is a major part. Okay, so we are looking for potential, I don't know, inefficiency in performance.
Uh-huh.
Okay, so I'd like to say something here too. So maybe everything happens in memory, and that's quite quick. But perhaps another source of problem is having to update everything all the way up to the root whenever you include something. I think there are inclusions in the tree often enough.
So all of the nodes need to have their height at least because of the balance.
This is right. This is unavoidable, I guess. But the size, I don't think it is. And whenever you include something in the tree, it doesn't mean that you have to update the heights all the way up, right? Only if the tree grows.
I think it's fast to do that. The problem will be to persist to this in the end of the algorithm.
Yeah, like sure, yeah, that part dominates for sure. But
yeah,
as I understand, you don't do this all the time.
The orphan, on deletion, it doesn't happen all the time. It would only happen, deletion from like the snapshot database would only happen, I think, if the user asked for it. But what does happen all the time is pruning from the recent database. But because that happens all in memory, it's relatively quick.
Okay.
Yeah.
We write to disk with every block, right?
Yeah.
No. Well, not with the pruning PR.
Not anymore. I see.
In the pruning PR, it's you only write to disk on
snapshots.
Yeah.
Uh-huh.
And then another question I had with the sorry, Ethan, you want to go?
No, please.
So with the lots of small writes, which are inevitably going to result in small writes to level DB, and is it true that level DB is a log structured merge tree? Okay.
I am not sure. I looked deeply.
Okay. So I guess my understanding of a log structured merge tree with small writes is, would it not result in like tons of writes to a write ahead log first? Those would be quick. but then it would essentially try and merge those in to larger, I guess they're called SS tables.
That's what I meant by the right amplification.
Yeah. So if we're amplifying before that, we're actually going to, there's a multiplicative relationship between the right amplification at the IAVL tree, as well as the level DB level because of the log structured merge tree. So we'd have to keep merging all those small rights that might be, would otherwise be eliminated, or what's the word, prove redundant. But I don't know if they can be before they have to keep getting merged into the. So there's, I guess I'm just echoing the concern that these small rights might be super expensive because of the relationship between the storage model that we have at the IAVL level and also at the level DB level.
Yeah. The main part of this, the large reason for this, the frequent writes, is because this 2 version keeps getting updated. So it's possible if there was a way to delete orphans correctly without having to update this 2 version every single time, then that might save us a lot of writes.
Yeah. So this is, so reading the specification for, so what we'd want, the Go level DB, so the Go IVL plus tree or the Go Merkle tree to do, or is this sort of like the specification for what we would want multiple implementations of a Cosmos SDK or Tendermint compatible Merkle tree to fulfill, just for orientation?
The orphans themselves are not something that is accessible to the API level, so it's not necessary that everything,
So
it's just what does matter is that a node exists so long as a tree references it, and then it gets deleted soon after no tree references it. So other than that, there's no requirement on how the orphan works.
Yeah, I think that's where I got confused, because it seems to me like there are a lot of specific implementation level details that are covered by the specification, which might not apply and maybe would ideally not apply to alternative implementations. So
Sure.
my question, like what level of generality are we looking to achieve in the spec?
Yeah. I was largely writing this in with the intention that someone who reads this would then be able to work on this specific repo itself and know what's going on, which I don't think was possible before.
Great.
So yeah, that was largely the goal, but I do think that's a good point that I should specify which of these things are at the user API level and which are lower level implementation details.
Cool.
Yeah.
And so with the pruning PR now, we only persist on snapshots. So does that mean we're only updating orphans on snapshots?
So recent DBs will still have their orphans. The recent DB itself also has orphans saved that are orphans in between 2 recent versions.
And why do we need to track those?
Well, you could.
We don't write those to the database, though, do we?
No.
To disk.
Those aren't written to disk. Those are written to the recent DB. I mean, it is largely to just delete the nodes immediately once all nodes are pruned. But that's the main reason.
Okay.
But you're right. Those orphans that are just between 2 recent versions, but not between a snapshot version, don't get written to disk, and that's a orphan only gets written to disk if the snapshot exists between a from version and the version.
But the 2 only really needs to be updated in the database on snapshots.
Correct.
Yeah, that's good. So have you actually? Sorry, this is kind of an aside, but have things been benchmarked between the The old AVL and the pruning, post pruning.
I've benchmarked it on like random input, which I don't think was particularly like useful. But I did see like different pruning strategies end up having like wildly different like efficiencies. So
Aditya, I know Bez has done a fairly extensive benchmarking of syncing the Cosmos hub from Genesis.
Yeah,
not really for this reason, but
yeah, that was my intention, is to like work off of his stuff. But I did kind of want to take some like reviews first before I went too far down that rabbit hole.
Cool, that's exciting.
Yeah. But yeah, I think the benchmarks would be much more useful if they were against like an actual blockchain like the Cosmos Hub.
I have a question quickly. I think I'm a bit confused. This version, when we delete an IAVL version, isn't it typically that we delete smaller versions and keep earlier versions?
Delete smaller versions? What do you mean by smaller? Like lower?
Lower, yes.
Yeah. Well, the deleting version stuff itself is like largely, that's exposed to the user, so they decide when they want to delete a specific version. But if the user passes in a pruning strategy, then the recent versions get deleted. So the oldest recent version gets deleted on each save version.
So, because we have this range from version to 2 version, and you're talking about a case when we delete the 2 version here.
Yes, yes.
And I'm wondering how typical that is in our scenarios on how we.
So the reason for that is because, so this would be like, let's say a node exists from version 5 to 8, and then the user deletes version 8, for example, and then the 2 version will be moved back, and then it'll just, the code will check if the 2 version has reached less than or equal to from version, and then if that happens, then the node itself is deleted. But yeah, if I guess in a typical use case, like it's possible that there is no from version. That's like there is no from version in the database itself. And if that happens, then the 2 version will get pushed back to the highest predecessor that exists. And the highest predecessor that exists was 0. And then the node will get deleted immediately. Does that make sense, or? Yeah. So it's like in like a use case where like we're deleting earliest versions first, so there doesn't exist a version before the version that gets deleted, then this 2 version will get pushed back all the way to 0, and then the node gets deleted immediately.
I was confused because with the other operation where we actually delete a full tree, not only a node.
This is deleting a full tree. When we delete a full tree, we delete the root hash and we delete any orphans that no longer get referenced by any of the trees. And we can track that by using this 2 version and from version.
Okay, then I'm still confused. Maybe we take it offline, because I thought when we delete trees, the oldest version of the tree, in a typical scenario, right? So we keep the latest, the last 100 versions, and when we clean up, we will clean the version with the smallest number. Yes,
that's for pruning, correct?
For pruning.
Yeah.
And is there a case where we delete an IAVL tree not for pruning purposes?
Only if the user called the delete version function.
Okay, so then this case where we are with the orphans with 2 version equals V is very rare. No?
Yes, I think so, yeah. Well, deleting versions from the snapshot database itself, it's like it would only be if the user called it.
Okay, please.
Okay. So this will, I think, clear up why the orphan format is this way specifically, because the way the delete orphans algorithm works is that we traverse over the orphans version. So we traverse over O and the 2 version. And then that will retrieve all nodes that got values in our database that got prefixed with O and the latest version -1. So this will retrieve all of the orphan hashes, and then we can delete the node if the predecessor is less than the from version, or if the from version is equal to the to version. So those are the 2 cases where we delete the node. And so you can see that code here. We delete it from our batch and then uncache it. Otherwise, we just have to update the key. And then in that case, we save the orphan with the hash, the from version, and then the new to version, which is the predecessor to the last to version. Does that make sense? I think it's just like the code for something I've already explained earlier up here. And then the pruning versions is how we automatically delete versions from our recent database. So on any save, we delete the oldest version that exists in the tree if our recent DB is already full, because our pruning strategy defines a specified number of recent versions that can stay in the mem database. And so, yeah, the IAVL version v minus strategy.keep recent will be deleted from the recent DB. And this happens on anytime you save a new version.
Is the pruning strategy just the keep recent parameter, or is there more involved?
It's just the keep recent parameter, which is how much to save in the pruning in the recent DB, and the keep every parameter, which is like the snapshot frequency.
Right.
Yeah. Okay, so that's.
And so, sorry. And so, ideally, a user would set a pruning strategy, and then that's it. They would never have to like manually call delete.
Nope.
Right.
They would never do it. Yeah.
Right.
Okay. So that was like all of the database documentation. Now, like the IAVL tree itself. So we can start with the immutable tree, which really is a pretty simple struct. All it stores is the root, the node database, which you can use the root with to retrieve all of the nodes inside that immutable tree, and then the version of the immutable tree itself. And then the IAVL tree also has getter functions like size and height to get the immutable tree's size and height. Cool. So there's like get functions where you can get by key, and then it will return both the index and the value. And the index here is if you sort the leaves lexicographically by key, what index does that node land in? That's the index that gets returned. And then you can also get by index, where you give it the index and you return the key and the value that is at that index of the sorted list of leaves. And the leaves are already sorted in the tree, so there's no additional sorting logic that happens.
Do we have proofs of the index?
I haven't written up the proof documentation yet, so I haven't like delved deep into the proof docs, but I can check.
Okay, maybe that's an aside, but it seems like it might change how I think about state sync.
Yeah, you're thinking about state sync, right, in the index.
Yeah.
Okay.
How is the index used? What can we do with this index?
How's the index used?
Yes.
We need to know for state sync not just what a node
is. Forget about state sync right now in the.
I think Zaki mentioned that it gets used in the range proofs, but I can double check. It's just a exposed function for the user. But I think Zaki had a specific answer for it. Oh, yeah. So it's efficient iteration over key ranges, I suppose, but I haven't looked in the proof docs yet, I mean the proof code yet, so I can't verify that for myself. Are there any other questions on how get works? Okay. And then the only other functions in the immutable tree are the iterator functions. So you can iterate and pass in a callback function, which takes in a key and a value and returns a Boolean. If it's and if this Boolean is ever false, then the iteration gets stopped. Or sorry, if the Boolean ever returns true, then the iteration is stopped. Otherwise, it'll continue. And you can iterate over a range of start and bytes and pass in whether you're ascending or descending. And then there's an iterate range inclusive function as well. That'll just iterate over the start and end inclusive. And then if you pass in start and end with nil and nil, then they'll iterate over all of the keys in the IAVL tree. Any questions on iteration? Okay. I think then like the last thing I wanted to go over was the mutable tree, which is what allows for any updates to happen between two IAVL trees. So
it looks like, sorry, I don't have an answer yet for what index is used for, but size is used for computing indexes, to answer Fernando's earlier question.
Cool. All right, thank you. So yeah, the mutable tree has the current working tree as just a like immutable tree that gets embedded. It's the last saved immutable tree, which is the last tree that got persisted either to the memDB or the level DB. An orphan map, which we talked about before, which is any nodes that got removed by changes to the working tree. And then a map of all of the versions that exist in the node DB. So you can just check in this versions map to quickly see if a version exists, and then the node DB itself, which gives you access to all of the nodes. Yeah. So anytime a version gets saved, versions V is set to true. Anytime it gets deleted, versions V is set to false. Are there any questions on like the structure itself?
Yeah, why the key for orphans is a string?
Because you can't save it with a byte. Oh, why is it a?
You can't use bytes as a key in maps in Go. So it's effectively the bytes just as a string.
What is this key?
It's the hash of the node, right?
It's in here. Let me double check that that's correct. Yeah, it's the hash of the node. Yeah. So the hash of the node is a byte slice, but you can't use a mutable key. And a byte slice is mutable. Yeah. So you just pass the hash into like a string conversion function, and then that gets saved as the key. Cool. So set is what we use to add a new key value pair to the IAVL tree, or to update an existing key with a new value. So yeah, it's a recursive function. So if the key is less than or equal to the root key, it'll recursively call set on the root's left child. Otherwise, it recursively calls set on the root's right child. And then it goes down the IAVL tree all the way until it reaches a leaf. And if the set key is less than the leaf key, then it'll create a new inner node with the key equal to the set key. because as we said, the inner node has the key equal to the rightmost key of the left branch. So that's the set key in our case. A height of 1 because it's an inner node that's the parent of leaf nodes. A size 2, and the left node is the new node that we just create with the new key and value. And the right node was the original leaf that we had. And then the version is the current working version, which is the latest version plus 1, because we're on like the current working tree. And then if the set key is greater than the leaf key, then we just add the new key to the right. So you see that these two values are flipped.
Well, sorry, the latest version here isn't the latest saved version. It's just the latest, whatever our latest working version is.
Correct. So it's the latest saved version plus 1.
It is the latest saved version.
Why would it be?
Like, does the version increase by 1 between snapshots or by whatever the number of heights between them was?
This has nothing to do with snapshots. It has to do with setting between, like, so on a saved version, the the current working tree gets put into the last saved value here, and then gets cloned and then put into the current working tree.
Right.
Yeah. And then
the version's incrementing.
We're talking about changes to the current working tree.
Right. So the version is incrementing with every height, no matter what, whether we're saving the disk or not.
Yes.
Yeah. Of course, it would have to because the pruning strategy can be subjective.
Correct.
Right.
Yeah. And so any node that gets recursed upon during a set call will get orphaned because either some child will have a new value, in which case the hash is changed, or it'll have a completely new descendant, in which case the hash is changed. So all the nodes that get touched by this recursive call get added into our orphan map. And so this works by just accumulating a list of orphans as it descends. And then, yeah, as was said earlier, after each set, the current working tree has its height and size recalculated. So this is a good point for why the size, it's not like it's a write to the database every time the size is recalculated, because all of this height and size recalculation is happening in memory, and then on the save version, the height and size are written to the database. So it's not as though we're updating the size of each node in the database all the time, if that makes sense. It only gets written on the commit. So multiple size updates in the same version don't get written as different writes to the database. Are there questions there, or?
Yeah, sorry, I'm wondering what my question is. So if you do an insert, then you need to rebalance, right? And do you first rebalance and then you do the height recalculation?
No. So first first what happens is that we simply insert naively with no balancing logic. And then after that insert, we calculate the height and size. And if we recalculate the height and size of every node, right? And so if the height of the left branch and the height of the right branch of the working tree differs by more than 1, then after that we rebalance. And then the rebalancing will possibly cause more orphans to be added. And then only after that we return.
Bigger or equal than 1?
Bigger than 1, not bigger than equal to.
Right, okay, perfect.
No, it can be only 2, right? Or minus 2.
2 or more.
Yeah, it'll only ever be 2 or minus 2 because we check immediately.
But if it's 1, then it's fine. We leave it like.
Yeah, because I don't think it's possible to fix a off by 1.
Yeah. Exactly.
Cool. So then remove. It's a recursive function that works largely in the same way. If the key that is trying to be removed doesn't exist, then remove is effectively a no-op. So again, it recurses down the IAVL tree in the same way that set happens. And if the leaf node key is equal to the root key, then the node is removed and all of its parents are recursively updated. And if not, the function just returns. Yeah, so this is like internal details that wouldn't matter for like a user API, but like to understand how the repo itself works, it has this recursive remove function that returns a bunch of different values. So the new hash, which is if a node in a recursive node's like subtree gets removed, the hash of that node will change. So this is the that's what this return value is returning. And if the node that's being returned is the node that got removed itself, then the new hash is just a nil. Yeah. So just like with set, any node that gets recursed upon on a successful remove, meaning that the key actually exists, will get orphaned. So replace node is like the new node that replaces the node that got recursed on. So yeah, if you see like this documentation here, like you have this node with a right leaf and a left leaf, and if the left leaf gets removed, it just has the IAVL tree pointing directly to the right leaf, and then so the replace node here is just the right leaf because there's no need for an inner node, and then the orphan node is the left leaf along with the original inner node. Yeah, and so it also returns the leftmost leaf key, and this is only used if the node that got recursed upon was the right child of its parents. And since inner nodes, since inner nodes should have their key equal to the leftmost key of their right branch, then this is just telling you what to update it with. And then the remove value is the value that the node, the value that actually got removed. So that gets returned on the remove function. So we need that. And then any orphans that got removed just get accumulated in the recursive call.
What do you mean it does not change as it travels up the recursive stack?
What does not change? Oh, the remove value? Yeah, because when I remove a specific key, that value needs to get returned. So as the return values bubble up in the recursive call, this value doesn't get updated on each recursive stack because we're trying to return the original value, right? So there's no need to change it on each recursive call. Okay. So the last part of this is how balancing works. So yeah, as I said before, the end, just as with set, on any remove, we calculate the height and size and then rebalance if necessary. Yeah, so this is how balance works. So we have like these two helper functions, rotate right and rotate left. So when we rotate right on a node, we orphan its left child, and then we set the new node's right hash to equal to the rotated node, and use the left child as like the new parent. So I think the visualization is a lot easier than any of the writing. So if we have this as the before, and we're trying to rotate right on 8, we move the left child, which is 4, up, and the 8 originally, we move it down to the right child of 4, and then we take the right child of 4, the original right child of 4, and move it into the left child of 8. So this is the before and after, and you can see it gets a bit more balanced. And then it's just the 4 node gets orphaned. And these are numbered to show that like the key order is still preserved, right? So all of the numbers on the left are less than or equal to all of the parent node, and all of the numbers on the right are greater than.
So what hashes do have to be recomputed here? It's not visible here, right?
4. 4 needs to get recomputed, and 8 also.
Okay.
Yeah. Because those get new left hashes and right hashes.
In the bottom, there's a typo, right? The 1 and 3 are swapped.
Yes, that's a typo.
Could you go back again at the Joseph's question? Why do you say orphaned 4?
Because 4 got its right hash changed.
4 is the node with the key 4 or number of nodes that are orphaned?
Yeah, 4 is the node with the key 4.
Oh, okay.
Yeah.
But remember, it's misleading because in the AVL plus tree, all the keys are actually pushed down.
Yeah. So these aren't actually node keys themselves. Like these are just labeled this way to show that like the key order is preserved. But yeah, it's like in an actual IAVL tree, this key would be like the key, the same as the key here, like this key.
Yes.
It's just I numbered them differently for like clarification.
Didn't 8 get orphaned too because it's
4 and 8 also had a new left hash. So yeah, that's correct. I actually think there needs to be an issue on that because I don't think that's how the balance function currently works. I think it works like this currently. But yeah, 8 also needs to get orphaned. Yeah, so the downside of like not doing that is that the balanced orphans stay in the database for longer than they should. Yeah, and then rotate left works the exact same way, but in reverse. So the right child becomes the new parent, and 2 becomes the left child of the parent, and the left child of the original 6 node gets moved into the right child of 2. So it's the same thing, but in reverse. So the IAVL detects whenever a subtree becomes unbalanced by 2. So whenever this does happen, the tree is immediately rebalanced. So because of this, any unbalanced subtree in the IAVL exists in basically 4 states. It can either exist in like this left-left unbalanced state where it's off by 2, but like the branch that is longer is on the left and then on the left again. So in this example. And so to fix this, we just call rotate left twice. We just call, rotate right on the node 8. And so we get back to a balanced AVL tree. So this is the left-left unbalanced case. In the left-right unbalanced case, we have the longest branch being first on the left and then on the right. And in this case, we first rotate left on node 4, and then that brings us to the left-left unbalanced case here. So we've changed this left-right unbalanced to a left-left unbalanced tree. And then we can just call, as we did before, a rotate right once on this 8 here, and then we can get back to a balanced tree. So those are 2 rotation calls. And then the right unbalanced case works the same way. We have a right-right case where all we have to do is rotate left once to get it balanced. And then a right-left case where we first have to rotate right on this subtree here, which will then make the whole tree right-right unbalanced. And then we balance it completely by rotating left on the parent node 2. And we get back to a balanced tree. Are there any questions on like the 4 different cases and how we rotate to get them balanced? Okay. So then, yeah, the last few things, save version. So once all the updates happen, we call save version on, let's say, the end of a block on a commit. And so it saves the current working tree as the latest version, tree.version +1. And then every now and then there can be like the root is empty, so like there are no nodes in the tree, so then we just save an empty root. But if there isn't, then we just save the root hash, basically called NodeDB's save version function. Then tree.version gets incremented. We update the versions map to versions tree.version equals true. And then, as I said before, it will set the last saved immutable tree to the current working tree, and then clone the working tree for the updates on the next block. And then resets the orphan map, and then it'll return the root hash. And then, yeah, if there is a custom pruning strategy, then as I said before, on every save version, we prune the oldest version that's in the recent DB. So this happens by just calling this prune recent versions function. That's defined in NodeDB.
Can I ask a question? It's not very clear to me. So the save version happens, you said, when we do a commit?
Yes.
So
on the commit of a block, yeah.
On a commit of a block. But before save version, if in a commit you have multiple keys that are changing, then for each key, or added or removed, for each operation, we perform the operation, we rebalance the tree, we go to the next key, we do the same thing. So the version could be increasing by 100, right?
No.
The previous.
No. The version doesn't increase by 100 because the tree version doesn't get updated on each set. So only like when we create a new node. So let's say we've saved tree version 10, and then we make 5 different sets, right? Those 5 different sets might create 5 new nodes, and each of those new nodes will have this new version, which is the latest version 10 plus 1. So it'll have all of those 5 new nodes that get added will have version 11.
Yes, okay, perfect.
Yeah.
Okay, but we do insert remove operation for each, and then rebalance after each. So if you have 100 things, you will rebalance 100 times.
Assuming each of those 100 changes caused it to get unbalanced by more than 1, yes. Yeah.
I think it's possible to balance multiple times in a row, right? Oh, of course it is, yeah. Depends where you insert in the tree. But if you're inserting into a spot that just got balanced, then it'll take at least 2 inserts to force a rebalance.
Yes. Yeah. Okay. And then the delete version, all it does here is just call the NodeDB's delete version function and delete the version from the versions map. And it's fairly simple, and it'll return an error if the version is either invalid or non-existent. So that's, oh, and yeah, the key thing to note about delete version is that it's unallowed to delete the latest version. So you can't delete, if you're on version 10, you can't delete version 10, but you can delete versions 9 to 0. Yep, so those are that's all of the documentation I have on the IAVL. Are there any questions, like overall?
Where do you calculate the hash of the node?
In this new node function, it'll get hashed there if it's a leaf node, because this, yeah, that's where the hash gets calculated. And then I think on the set functions as well, like it'll recalculate the hash on the recursive calls for any changes. So set and remove will recalculate the hashes of the inner nodes.
And sorry, go ahead.
Yeah, I was wondering if you could calculate the hash only in the end when you commit the tree.
Well, on 2.
Isn't that what we do? We only hash when we save the tree?
Yeah, that might actually be true. Let me double check.
Yeah, I think I read something like that there.
Yeah, the recursive set. Sorry, the recursive set recalculates the height and size.
Right.
Yeah.
Because it might have to balance, but
but the hashes themselves, you're correct, don't have to change.
They only happen on commit.
Yeah.
And with the pruning strategy, if you set, you set your keep every 100,000 blocks, and then keep the most recent 10.
Mm-hmm.
So with every block you commit, you'll delete the 11th, like the 11th last one, and keep the last 10. Or you say it was just keep one, but then it keeps every 100,000, and it keeps those around forever. So those old snapshots will never get deleted.
Correct.
Yeah.
Unless the user manually goes.
Unless they manually go and do it. But if they manually go and do it, they're going to have to copy over all the nodes. Like it's going to orphan a ton of nodes that are going to be referenced by a later snapshot. So it'll create a huge write.
Yeah, but I'm not sure if you have your frequency that high, I'm not sure how many nodes will be in common between node 100,000 and node 200,000.
Yeah, fair enough.
100,000 in version 200,000.
Yeah, okay.
So the orphan map may actually be pretty small.
Okay.
But again, you would need benchmarking on an actual.
Yeah, it depends on the use case. Yeah. Cool. Who has questions? Surely there are questions. Everyone's a master of the AVL tree now?
I have not a question maybe, but some suggestion. So
Sure.
this is a very, very good description on what is there now and how it works. It gives a very, very good overview. But I wonder if we shouldn't have some a design document or ADR. It's retroactively explaining why the choices that were made make sense, because why do we even need a self-balancing tree? It could be a sparse Merkle tree, or what is the criteria the tree needs to fulfill? Why the design choices make sense? This is completely missing, for me at least, to understand why do we need orphans. Isn't there a different concept that could fulfill the same things? Why do we there's so many questions like this, and there's no explanation why the design choices were made as they were made.
Yeah, I agree. That would be super helpful. So
yeah, we did do a dev session on this problem many months back. So that's hosted online. So there's a lot of content in there that we can potentially call from. So between answers there and question answers here, we could probably put that together. But it definitely would be really valuable to have that.
Yeah, I would also like to echo what Ishmael was saying, specifically just praising how thorough the documentation is for the IAVL tree now. And I personally understand more in this session than I ever thought I would, even after reading the code. So thank you for that, really. Aditya, in your mind, what are the next steps that you'd like to take?
For the IAVL specifically, because I still feel I haven't fully fleshed out the pruning PR, I definitely want to get better benchmarks against a more useful blockchain than just the random stuff that I've been doing, just random sets and deletes, because that didn't give me much useful information. And then from there, I've been talking to Dave a bit about his ideas.
The author of the IAVL tree in Rust.
I don't want to do that, but.
Sorry. Who's Dave?
I mean, he was talking about again, going back to whether these design decisions make sense. I think revisiting that is really important. Does it need to be immutable, for example? And then fleshing out why things are an AVL tree rather than a sparse Merkle tree, I think is probably the next step, documentation-wise.
So Matt Bell from Nomic did, for completeness, did rewrite an AVL tree in Rust. slightly different than ours, and some of the design decisions were made differently. Like instead of all the orphaning and snapshotting happening in the implementation, it just uses the underlying RocksDB, which means that means that nodes, the leaves can actually be stored directly under their actual key in the database. So you can iterate over the database directly rather than needing to go through all the intermediate nodes which are indexed under their hashes. It eliminates all of that write amplification that comes from like rewriting every node every time a child changes. So it seems like it's an order of magnitude or two faster.
Okay, that's interesting.
But it's
Can
not.
You pass this?
Sorry?
Yeah. Sorry, can you pass this repository in the chat? Because I started also a Rust repository.
Sure.
With this. There you go.
My mouse stopped working, so I'll have to do it later.
Okay, no worry.
God damn.
About the benchmark, I was running some tests. I downloaded all the Ethereum accounts. I tried to store them all in the Go implementation in the AVL. And it was really slow for all of them. I never even completed the whole data set, but I can send you the test and the
this is you benchmarked against master, correct?
Sorry, what?
You benchmarked against the master branch?
Yeah. Yes.
Okay. Yeah.
Is there any other branch that?
Yeah, the pruning, like I was specifically talking about benchmarking different pruning strategies, and that hasn't been merged yet. So, yeah, 150.
But I think the time that
the benchmarking there would only matter if you were doing it over like thousands of blocks, seeing the comparison.
Oh, okay. Yeah. I was testing just one.
Yeah. Right. Like, so you're saying you didn't even get to like a single commit thing because it was just adding to the machine so slow?
No, adding is fast, but saving to disk is really slow.
Yeah. Yeah. Okay.
And
the pruning PR wouldn't help with that.
Yeah, exactly. And then I can maybe talk about what I've been doing. So the idea that we had was to save some blocks of in the leaves instead of having just one leaf. You can save like a chunk of leaves. And then I did some benchmarks also, and it was much faster, of course, because those are, if you save a chunk of leaf, you just require one read, and then you get a lot of keys. So to read the whole data set is really fast. But now we were working with trying to do this on the fly. So saving these chunks on the fly, also rotating the chunks and merging them together. And that's taking a bit more time than the simple case, which I just duplicated all the chunks, all the leaves in these chunks. But that really saved time on to sync to read all the database, because you do few reads basically.
Okay, cool. So like in the database, it's like rather than saving each leaf individually, you're chunking them and saving them. Is that correct? Or?
Yes.
Okay.
So yeah.
But does that mean that a light client who wants to verify a leaf needs the whole chunk of leaves, or is this just the way they're stored in the database?
Yes, I think the idea would be that it needs the chunk.
It needs the chunk. Why do you say that's the ideal?
Because you only have the chunk saved on the database.
But is there a way for the chunking to be like an implementation detail so that a light client who's verifying a particular leaf doesn't need the whole chunk? They only need you know, the full node might have to load the chunk from memory or from disk to actually put together the proof. But if the light client doesn't need the whole chunk, that might be nice. But you know, then that might compromise the structure you're working with. You know what I mean?
Yeah, I was thinking. Yeah, I don't know. I have to think a bit.
Like you could imagine doing something like it broke, like using a simple Merkle tree for those chunks, so that you can store a bunch of leaves in a chunk together, and then the hash of the chunk is actually a Merkle root of the different leaves in the chunk, and that way when you give it to a light client, not like a Merkle root like an IAVL Merkle root, but just like a very simple Merkle root.
Yeah.
And then
no, but in this case you can just use the same AVL structure. You don't need another Merkle tree.
Sure. Yeah,
I think you can do that because you can
just compute the hash without using all the database stuff.
Yeah.
Yeah, that makes sense.
Cool.
Another thing that could be is like you can actually store, you know, I think if I understand correctly, the kind of optimizations that Alexei was working on in TurboGeth, he would store multiple nodes together in the database, so that even though there was this tree structure and you had to kind of, you know, traverse the tree, when you do a lookup, you didn't have to do the lookups one node at a time. You would do a lookup and it would load a bunch of the nodes kind of together for you to reduce the number of reads from disk. So that's also kind of an interesting implementation detail optimization.
But in the AVL case, it's interesting. You don't need to store the whole just with the keys, just with the leaves. I mean, you can reconstruct the AVL if you store them in order. So because the keys the leaves are replicated up in the tree, some of them. So if you know their height, you can reconstruct the subtree of this chunk.
Are you sure you can do that without knowing the insertion order? There's enough information in the tree?
Yeah. Huh. Yeah. Later, I thought about the first experiment I did was with the insertion order, but that is not enough because in the rotations that you have to recompute the insertion. But with the height is really easy to see. If you just think like if you have a chunk, you go from the highest height, inserting the leaves, the inner nodes, I mean, and then in the end you insert the leaves. And then you get and then all you need to do, you can even do this in parallel. That's what we were thinking.
Wait, sorry, no, I didn't understand that. If you only have the leaves, how can you be guaranteed to recompute the tree? Are you saying you have some of the inner nodes?
Oh, yeah. No. So you have the leaves and the height that the leaf is in the subtree, in the subtree. So you don't even need the height. You need just the order. So if this chunk is ordered as the keys appear, then you can reconstruct it.
Right. By order, you mean more than like the lexicographic order. You mean like the actual order in the tree.
Yeah, the actual order in the tree.
Yeah, right. Cool. I posted the link, by the way, to Nomics Rust Merkle tree.
Thanks.
Just time permitting, should we...
Aditya, we can still see your screen, so...
Oh, okay. Do you want me to try talking about the pruning PR real quick, or 20 minutes?
Marco, what were you going to say?
I was going to say, since we don't have enough time, we can just discuss state sync and possibly the next steps to take
in the near term with state sync. We all have a better understanding of the IAVL tree right now. Sorry for that. So I think we would be able to review the pruning PR with better comprehension. But the state sync discussions, I think, is like the hot topic and the most.
So I've recently convinced myself that all solutions are bad. No, not really. What I think I have discovered, and maybe I'm calling into question because of this index stuff, is that any approach based on chunking will not be sound, or will have, basically we'll have termination issues, potential termination issues, because we don't have proofs of the chunks. Like, we can't provably know that a chunk was like correctly generated. Even if all the leaves and nodes in the chunk verify in the tree, we don't know that, like, this actually was chunk 3 that we asked for. And so unless there is something with respect to the provability of those indexes, which there may be, I kind of forgot about them and haven't thought about them, but they also might not generalize, we may need to go with the kind of key-based thing, kind of like what Jay was suggesting, which has the downside that in the worst case, we might just having to read random ranges from the tree. And so that might be just slow, but probably not untenable. Did everyone understand what I just said?
I think there's a lot of context to what you said in terms of understanding state sync, in terms of the chunking algorithm. I'm not sure where everyone is in terms of catching up on the ADRs. I'd be curious, who has time to work on state sync? Would like to maybe be part of like a tighter group. So this might be where state sync is at. It seems to be under-resourced.
It's heavily under-resourced at this current point. On the Tendermint side, from AIB side, we are currently working on hiring, but of course, the people that are hired in the near term won't be able to come on board and do something of the magnitude that is state sync.
Yeah. So what is is there a short-term solution where we can support something like the Binance PR? Is there a way for their solution to be injected so that people can run, so that we can like compile Tendermint nodes that have that?
Couldn't they do it? Couldn't we run it with the custom reactors, adding in custom reactors or replacing core reactors feature we released in like 32.2?
I don't know. That's what I'm asking. Can we use? Does that work?
We previously had this discussion about the Binance PR, and the last time that we visited this question, the answer was we should not merge. So are we now looking to revisit?
No, not merge. Just make sure that it's possible for people to compile Tendermint with that reactor without forking.
Okay.
They might have to fork the
code base.
The SDK. Well, no, it depends what they're trying to achieve. No, they shouldn't have to fork Tendermint. The goal is maybe you have your own repo and it imports from Tendermint and it imports from Binance's thing, I guess their fork of Tendermint. and then you get, the current latest Tendermint with an implementation of the state sync from Binance. And then how that would end up in Gaia is, I guess, a secondary.
Gaia would need to support the ABCI methods, right?
I don't think they have any changes to the ABCI.
No, they must have.
How do you get? Yeah,
they must have changed ABCI. In which case, it's probably not going to work with the generic reactor thing. Yeah, so maybe this is why this fell over originally, because of the ABCI changes. Yeah.
So definitely nice to be able to have some support for the Binance PR, at least as an intermediate solution.
Yeah.
Does anyone have the resources to look at the Binance PR and look at like a reasonable integration path to forking Tendermint and running it with that code included? Bueller? Anyone?
Who's Euler?
Sorry, bad reference. So it just seems to be like we don't have the capacity to do this. So is there anything that we are doing now that we want to stop doing and work on state sync instead?
Well, the idea is to wrap up the blockchain reactor stuff so that we can move to state sync.
Yeah.
Yeah.
Okay, that makes sense to me.
The light client is more blocking than state sync is. Just so you all understand.
For sure.
It is a rational understanding of current priorities that light client needs to be the biggest pain point. I also think the pruning IAVL changes, if we could get them in, would massively increase the speed of syncing.
And Zaki, what is your take on the commit size reduction and having that go out to the hub at some point?
I'm support it. I don't. After we do hub update 3, I don't know when we're going to do another hub update anytime soon.
But does it make sense to try to schedule a hub update that only updates like Tendermint and doesn't have Gaia changes, or do you think we should like package them together with whatever the next one is?
The next one is IBC, but
the next one is probably IBC.
Right.
I would vote from a technical side for separating the updates. From an organizational side, that costs time. I don't know what the trade-off is.
I would also vote for separating them, but it would mean the commit update would happen. It could happen probably pretty soon. Like even up, say, a month after the.
I do think that an update that basically has no API breakage and is just like effectively a state dump and restart would be much less painful for the community in general.
Right. It would have some breakage because the vote structure in the RPC in the block, like in the commit, would change. We could actually probably keep that the same. We could probably do it without breaking the RPC. It would just be more work, but it would also be nice to break the RPC because then all the clients will benefit from the size reduction as well. But it's obviously not as big a deal.
I do believe the RPC.
I mean, when you're talking about who gets broken by that, it's like the block explorers.
It's the block explorers, yeah.
Which is not as painful as breaking the exchanges.
Right. It also depends on how they've written their code, in which case it may not break them at all. But anyway. So yeah, maybe we should start. I can open up like a forum discussion about that and start gathering larger community feedback to see what folks think. But it does sound like that and the pruning and the light client are all higher priority than state sync per se. And so if we get all those done and wrap up the work on the blockchain reactor, we'll be in a position to get back to state sync.
Yep.
If the total design of state sync is clear, and let's say the chunking ADR is out and we kind of have a better understanding of how we want to move forward in terms of the design, would it be if we're still under-resourced in, let's say, a month, would the consideration of kind of farming it out to a dev house that we work closely with
totally
be an?
Yeah, I think so. I think my conclusion from the latest kind of chunking work, architectural work, is that it's actually not really feasible if we want the kind of real-time soundness. Like if we don't want to potentially compromise termination or have to restart all over again once you've synced a lot of stuff, in which case we kind of have to flesh out something along the lines of the proposal Jay had made with syncing key ranges. And then, our Merkle store is going to need to be able to do random reads, which it can. It just might be slow. And it means people won't be able to cache as much if there are attacks going on. But maybe it's time to write up that summary.
Should, since that's kind of like on top of everyone's mind after today's call, should we aim for Monday's review session to be based on tree chunking to review the tree chunking PR, and then it kind of gives you some time to put it into an ADR format?
Sure. I was thinking of actually making a folder for StateSync ADR documentation, since we're kind of accumulating a lot and I don't know how to necessarily organize it all into one document. And
you want to put it in the spec repo under like the StateSync under spec?
No, I don't think it belongs there yet.
Okay.
When we get a proper spec, maybe we can get that into there. But meanwhile, it's just like architectural deliberation.
Do we have an RFC folder inside the spec repo? Yeah.
Yes.
So that's a good.
Would it go under RFC?
Yeah, maybe. Yeah. Okay. So we can set that up. Yeah. Great.
Yeah. So far, only blockchain consensus and the ABCI specs have been moved, and then slowly move over the rest, and then of course documentation CI changes.
Mm-hmm. Yeah, this is going to change a bunch of build stuff, right? Because now the Tendermint's going to depend on the spec repo.
Yeah. It shouldn't be a problem. We're going to redesign the entire deploying of docs in the coming weeks before the new Tendermint, so it would all be fixed.
Cool.
So are we putting the StateSync a bit on hold, or we want to wrap up like the current understanding and wait to have resources to restart work on this?
I think it'll continue kind of at the same pace. It sounds like we need to finish up the blockchain reactor stuff to actually be able to start working on it. And I think it's, in some sense, it's blocking on that work because we want to have like a cleaner reactor framework for building it in. So once that stuff wraps up, we can reevaluate starting work on StateSync again. But meanwhile, we should actually try to, finish a design or go back to fleshing out the design.
But like, if we don't have resources to work on this, like this design seems to be the biggest issue.
Yeah.
We don't know how to do this thing. So I'm wondering like if it's, if this is really the best way to be productive regarding this thing, that we are kind of partially attacking it from time to time with the minimal resources, and we are just discovering more and more issues.
So I guess we
don't have resources on the dev side in terms of like research discussions and kind of design discussions. Is that also part of the under-resourced category?
Yeah, exactly. Yeah, we are essentially all looking more or less at a like line right now. And apart from essentially what Niki and Fernando are working, which is external people, I don't think that internally we have anyone who can really devote time for this right now.
Mm-hmm.
That's the problem. So that I'm kind of I don't like this thing that we are. It's super hard, and it's looked like we are not able to really make things more concrete. And we had like a few tries and have been very fruitful and interesting discussion, but we are still not able to move it, forward. And it's probably because just we don't have enough resources. And so I'm wondering if it makes more sense to try to kind of to make a small pause until we have resources, and then to really attack it properly.
Sure. That probably makes sense.
I mean, I think that makes sense, instead of just bringing it up. And then I think we need to set reasonable expectations for how our resources are allocated and where we want to be.
Mm-hmm.
And so I think the conclusion, I'm hoping the conclusion of this discussion will be like a reset of expectations from StateSync,
mm-hmm.
that we all know that we're not working on it, that we're working on other things, and that we're all okay with the priorities as they are.
Mm-hmm.
And if we're not okay with the priorities, then we could always adjust them collectively.
Mm-hmm. Cool.
The lack of StateSync doesn't really seem to be affecting anyone.
Right. Everyone's going to be running dump
It's true,
states anyway.
but it's hard to predict when things might become popular, and it might become an immediate problem for nodes joining the network.
But we have all these
There
other,
are basically,
we have a ton of other measures right now, right? That will help all that.
Yeah, that's true.
Yeah.
The light client will help in practice.
Yeah.
Because most nodes don't need to sync the full state as full nodes.
Yeah.
So.
Cool. Okay, so I'll start trying to push forward discussion on the commit reduction and see if there's interest in doing another update for that sooner than later, and that will help take a lot of pressure off. There's so much redundant data in those blocks; it's ridiculous.
Sounds great. It will cut the time of the snark verification of Tendermint light client proofs quite a bit.
Right. Yep. So we should work on that instead, snarks. That was the agreement here.
I talked to Cello's cryptographer.
Yeah.
Kobe.
2 days ago, and I'll try to work with him. I think.
I'm trying to find we're trying to like figure out a way that we can participate in their crypto calls, just to like work on it. I mean, so they don't verify the entire block header. All they do is they verify the signatures and the next validator set hash, which becomes like a Peterson commitment essentially. That's all they do.
Yeah, I don't know if we'll end up using the exact same circuit, but it seems like it will be similar, and maybe we'll succeed in convincing them to just switch to Tendermint. So who knows?
I mean, they want to switch to hot stuff.
Mm-hmm.
Yeah, so we can make Tendermint hot stuff compatible, and then everybody wins.
We just need to implement ADR30.
Is ADR30 make Tendermint hot stuff?
No, it just refactors the consensus reactor, and then we're at a point at that stage where it's more swappable, so people could swap out Tendermint consensus for.
When people say they want hot stuff, do they say they don't want to wait a timeout at the end of a round? Is that what they mean?
They want to go to one message and no timeout.
I think it's the pipelining more than the
pipelining.
But pipeline hot stuff and hot stuff, I think, are two different things.
Yeah.
Right, but Facebook's implementation, as I understand, has pipelining.
Yeah, but Cello's doesn't.
Right.
Is it for performance reasons or for correctness reasons or understandability reasons? Because like if it's for
understandability reasons, I think.
Okay. Okay. That makes sense. Because for performance, we are anyway terminating around 0. So timeout is almost never fired. So, but understandability, that might make sense.
Cool.
Cool.
Okay, so we're all in agreement for Monday. Should we not do the tree chunking then, and then do a review session most likely of the blockchain reactor? If we can, otherwise we can do a review session of something else.
Well, what's the state of the Go light client work? Anton, have you had a chance to work on that more? Anton still here?
No, he's not.
Nope.
He has a PR open right now. He took the recommendation of starting from scratch, and he has an MVP version. I'm not sure an update on where, on what stage of usability it is.
Okay. So we should probably try to push forward. We should probably continue focusing on the light client work and the stage of implementations.
Okay, then I guess we can also do, I believe Anton's taking some design from what you guys are doing with the Rust implementation.
A little bit, yeah.
We can.
I mean, it sounds like the main thing we need to figure out, is Chris still here?
I think he just stepped off for the IBC.
Oh yeah, we're over time. Okay, but yeah, let's take this all up on Monday and try to focus on light client related stuff, and especially what the kind of dependency graph of the different development trajectories are, so that we can maximally unblock things in the short term. It's just a matter of getting some APIs done for IBC development to continue moving forward. That should be quite easy to do without dealing with all these tough questions around our evidence handling and fork accountability crap. And then we can continue, laying out a roadmap for those items too, which are going to take time.
Okay, perfect. So more of a Mondays kind of planning, and then the blood client, we may be able to fit in a review of the Go implementation.
Sure.
Good.
Cool. All right. That was great. I'll stop. I should have stopped the recording a while ago, but I want to thank Aditya for really great work on the documentation and helping everyone come to understand that. And so thanks a lot. And we'll see you all later.
Ciao, ciao.
See you. Thanks a lot, Aditya.
Bye, guys.
Bye.